welcome everyone. Thanks for coming to John's candidacy exam. So he's done a pretty good job of already writing his title on the board because he's probably thinking I would have forgotten it. A Journey into Outer Space.
I wasn't, I swear.
Yeah. A Journey into Outer Space.
Okay, so first of all, thank you all for coming. So my goal of research is to create an analog for outer space for right-angled Coxeter groups. So an outer space in general is just a contractible space that a group's outer automorphism group can act on properly. In this talk, I'm just going to start going over roughly the history of what brought me to this topic, what started my interest in outer automorphism groups and the like, what things in the literature I've started studying as a source for ideas and approaches to take, and then finally the overall plan of attack I've developed so far to attack the problem with. So all of this started when I read a paper with an obscenely long title. The automorphism group of a graph product with no sill. So this was by So this is by Ruth Charney, Kim, and two of Ruth Charney's graduate students, Nate Stambaugh and Anna Vajayan. And in it, they study the automorphism group of a graph product, and under certain conditions, they show that the outer automorphism group, a certain subgroup of the automorphism group acts nicely on a certain space. So let's just go through the various terms we use here just to get everyone up to speed. So first, a graph product. So we start with a finite simplicial graph. And we label every vertex with some group, which we're going to call GV for the vertex V. So for the rest of the talk, all of our vertex groups that we talk about here are always going to be finite cyclic. In the paper in question, they also consider the infinite cyclic case, and you can have a mix of the two. But since my eventual goal is dealing with right-angled Coxeter groups, I only really care about the finite cyclic case. So the graph product of this labeled graph is the free product of all of our vertex groups. Sorry. And then we add commutator relations between any two groups when their vertices are adjacent. So the graph product in general is just interpolating between the free product and the direct product. The free product is just a graph product where we have no edges, and the direct product is a graph product where we have a complete graph. And the graph product just gets us everything else in between. So, if we're considering the case where we only have finite cyclic groups, we see that if we make all of the groups just Z mod 2Z, we get all right-angled Coxeter groups. In addition, if we were to consider the infinite cyclic case, if all of our vertex groups are infinite cyclic, we get all right-angled Artin groups and thus free groups.
So by these two groups commuting, you mean that every element in V
commutes with every element in GW, yeah. Okay, so for what we're looking at with only finite cyclic groups, we sort of have a natural generalization from the Davis complex to give a space for these groups to act on. The Davis complex, so we already said that Coxeter groups are one of these. So the Davis complex is a nice space for Coxeter groups to act on, where they're just basically acting by reflections. Well, finite cyclic groups of higher order we can just think of as rotations, and that's exactly how we generalize to get a space for them. So let's go over one example of this. 2, 3. So our strict fundamental domain for this action is going to be exactly the same as if this were a Coxeter group. So That'll be this. Then, now when we go and actually have the group translate this around to get our full complex, though, that's where things are going to look a bit different. So for our reflection groups, our order 2 groups, we're still going to reflect in exactly the same way we would for the Coxeter group case. And for our order 3 group, we're going to think of that as just an order 3 rotation. So that's why we're going to get this 3-pronged thing here. And we would just continue this over and over again to get the full Davis complex for this. It's roughly the same idea, so it's nothing terribly new. In a paper from 1998, Davis goes and shows that all graph products of this nature, the space that we just constructed here, has a natural structure of a building, and every building has a geometric realization that's cat 0. Thus, all of these graph products that we're studying here are cat 0. Now, from the title of the paper, we don't really want to study these graph products, though. We want to go and look at their automorphism groups.
So can you explain how you got from that thing?
From
Can you
this
explain
thing?
how the construction of both those objects and how you got from one to the other?
Okay, so here we're just taking, so so to get from our graph to here, we're doing the same thing we normally would with the Davis complex. We're taking that, our graph, we're going to flagify it. So in this case, we don't have to do that. It's already a flag complex. And then we're going to take this to be the link of any vertex. So that gets us right down to here, since we would have here. Actually, they have colors, don't they? So the length of this vertex right here is going to be equal to our graph, exactly equal to our graph. And then to get from here to here, we're thinking of these edges and then this vertex as fixed points for our generators.
You just made that the link of one vertex.
Right. Yeah. So yes, yeah. These really shouldn't be vertices in the same sense. But we can think of these parts of this piece of a cube. This isn't really a full cube. As these are the fixed point sets of this generator, this is the fixed point set of this generator, and then this over here would be the fixed point set of this generator. And then we're going to just have them act these by reflections and this by rotations. So here we're just going to reflect this way. We need to commute, so we continue going around so that if we call this A and B will commute here. And then here we want to be able to just rotate this around with order 3. So that's why we're going to rotate, rotate, rotate.
And now all the vertices in that
Complex have link this.
Oh, I see. So that was just your tool to get to.
Right, yeah.
Okay.
Yeah. Yeah, well, I wasn't building this the same way as we did in your class with just the regular Davis complex, mostly because the description given in this paper and in Davis's paper, when we're generalizing to just any order groups, it doesn't work well the same way. We can't just, say, okay, here's the n cube and blah, blah, blah.
No,
blah,
I
blah.
just didn't. That's the Davis complex, and that's your tool to get to the Davis complex.
Right.
Okay.
Yeah. Yeah. When I say Davis complex any other time in this talk, I mean this sort of thing.
Cover.
Yeah, the universal cover, not the n cube taking the faces the way we're supposed to.
Okay.
Yeah.
Can you just explain the picture, the right-hand picture?
Yeah. Okay. So.
I mean, are you literally saying that you're going to square with a cross in it as part of the thing?
Those aren't vertices.
No, those aren't vertices and edges. Those are just showing where those are outlines of the strict fundamental domain. They're not actual cells in the complex. Does that make sense?
Probably does. It's losing me with something.
Why don't you say formally how you construct that?
This?
The whole thing. You start with the.
Okay, so I start with this group.
Mhm.
I start with this graph. And then I construct a cell complex with a single vertex such that the link of that vertex is equal to my graph after I have flagified it. In this case, I don't have to do that. It's already a flag complex. So that gets me here. So this...
It's actually a cube complex.
Yeah, a cube complex.
It's not just a cell complex.
Yeah. So let me draw it this way so it's clear. So I only have one vertex here. Okay? Then I'm treating basically sort of the I don't want to say n since that has an actual meaning here, but
Okay, so you add a cube, here's what you do, you add a cube
Cube.
for each, you added 2 cubes for each
Two
cell,
site,
or
yeah.
1 cell, n plus 1 cube for each n
Cell.
cell in your graph, in your flagified graph,
yes,
and you put that next to your thing, this is going to make the correct link for that
Right.
particular vertex, and then you add and that's the same, so we added a 1 cell for that 0 cell
Yeah.
in this graph. Okay, so that's the algorithm, you do that
Yeah.
all around that thing. And then, when there's a reflection corresponding to those things, he reflects.
I reflect over it
So
and
then
that
it
gets
takes
me
the
here.
universal cover.
You're treating those outside edges as reflection.
As reflection walls, and these as rotation centers, basically. Make sense? Okay.
Enough that you should go
What?
on. Enough that you should go on.
Okay.
So all the squares you've drawn are filled in?
Yes, yeah, every square I have drawn is filled in. It's not an empty square.
So you added an n cube whenever you have a n minus one cell in your
Yeah.
flagified
Yes.
complex.
Yes.
Okay.
Yeah. I just had to make sure that was going the right way. Yeah. Okay. So now that we have a good handle on this, we want to actually start looking at the full automorphism group of this. So, in 2 papers, Lawrence from 95 and Corridor Gutierrez. This is Mo in 09. We find a nice generating set for the automorphism group of a graph product of finite cyclic groups. So this is going to be generated by 4 different types of automorphisms. So the first type are vertex isomorphisms. These are just isomorphisms of a particular, this is going to be an automorphism of a particular vertex group that leaves everything else fixed. And we're also going to have graph symmetries, so symmetries of our labeled defining graph. So these two together are just going to give us a group that we're going to denote as sigma gamma, and this is going to be just some nice little finite group. These are going to commute with each other, and they're all finite order. It's finite, everything's finite and happy. The next type we have are what we call transvections. So I'm going to abuse notation a little bit and refer to the generator of a group at vertex V with just that vertex V. So a transvection is an automorphism that sends V to either VWK or WKV, one or the other, under the following conditions. Okay, so we have a transvection that's permissible between 2 vertices if they're both of prime power order for the same prime. Our k that we're going to use here is just going to be either 1 or just the smallest common power, and that the star of v is contained in the star of w in our defining graph gamma. So this is a very restrictive condition. Even if we're in the case of just a right-angled Coxeter group, so we can pretty much ignore all of this gobbledygook because all of our orders are the same, so we're good. The star of V contained in the star of W is only going to happen sometimes. You know, there are lots and lots of graphs that we can draw very easily, especially if we have like a free product or something like that, where that's just simply not going to ever be true. So in the case of, now, if we move to the case where we have infinite cyclic groups, then the condition for permissible transvections becomes something incredibly different. But for our purposes here, this is a very restrictive condition, and for the most part, we really aren't going to, because it's so restrictive, we're not really going to care quite so much about transvections. What we are going to care about, though, are our last type of automorphism, partial conjugations. So a partial conjugation is going to be denoted by pi of vertex V and a component C, where C is a component of gamma minus the star of V. So we pick any vertex in our graph, V, we remove its star, and we're going to be left with a bunch of components. For each component, we're going to get a partial conjugation. And what this is going to do to some other vertex, or some other generator, we can think of it as, is it's either going to leave it alone if that vertex is not in our connected component, or we're going to conjugate it by V if we are in the same connected, if we are in the given connected component. Okay, so hence partial conjugation. It's part of conjugating the entire group by that vertex V. So there are a bunch of things we can see right off the bat just from the definition of partial conjugation. We can come up with some pretty simple combinatorial conditions on gamma and on the relations between different vertices and the like to tell when partial conjugations are going to commute with each other. We can also see that if we just take all of the partial conjugations for a given vertex V, that's the inner automorphism associated with that generator. So if we just look at the subgroup of aut generated just by partial conjugations, that's going to contain the inner automorphism group. Okay, so now a few other results by Mo, Adam Piggott, and Kim from 09. We have the following two nice results. So aut PC, the automorphism group generated by partial conjugations, is going to be finite index in the full automorphism group. If I'm recalling rightly, this is not true in general. This is only true if we have finite cyclic groups. Once we go to infinite cyclic, this is definitely no longer the case because transvections become a huge deal there. And the other nice thing that we get is that this group has a nice semi-direct product decomposition. Okay, so in for our group is just going to be the group mod at center. It's the center of one of these groups is going to be generated by vertices that are adjacent to everything. And if we were to just do that quotient anyway, we would just get another slightly different graph product of finite cyclic groups. So regardless of whether we have a center or not, is just going to be, again, a graph product of finite cyclic groups. It might be the same one, probably, or it might be a different one. But regardless, this is pretty easy to understand. We've got a good handle on these already. So if we want to study the automorphism group, we can pass to a finite index subgroup by studying this. And if we want to study the aut PC, the outer automorphism group is really where all of the interesting stuff is going to be happening. Make sense? Okay. So that's most of the words that are in this title. So now just the very last condition, the idea of a CIL. Oh, yes, it does work. Good. And it's inertial proof gamma has a intersection Okay, so a finite simplicial graph has a separating intersection of links if we can find a pair of vertices such that they that are non-adjacent, such that the intersection of their links separates the graph, leaving a component that contains neither of our original vertices. Okay? So this is a bit of a strange way of putting things, at least to hear it, but once we have some examples, it becomes really clear really fast. So, let's take this graph. This graph has a sill. If I take V to be one vertex, W to be another, the intersection of their links is trivial, so I can just take that last remaining vertex. There's my component containing neither of them. Hooray, I have a sill. Next. So, if we have a free product for our defining graph, we see that as long as we have three or more components, three or more groups that we're taking the free product of, we're always going to have a sill. So any results of this paper are not going to be helpful for us. Now a connected case. So this also has a sill. If I take V and W to be any of these sort of leaf vertices, the intersection of their links is going to be the vertex right in the center. I remove that, and I'm left with this component that contains neither V nor W, and again, I have a sill. So now, an example that doesn't have a sill. 2, 3, 4, yes, 5. Okay, so if I pick any two vertices in this path, the intersection of their links is either going to be nothing, or it's going to be the vertex directly in between them. If I remove that vertex, I'll be left with exactly two components, one containing V and one containing W. So this has no sill. So now we've got the basis of what's going on here. What the paper actually goes and proves is that in the case that we have a graph product of cyclic groups with no sill, our outer automorphism group is going to be finite. And at that point, it's kind of boring. It's going to be finite, and it also proves that it's going to be abelian, if I'm remembering correctly.
So what's the algebraic consequences of no sills? It means that these partial conjugations are...
It means that so we already know that the partial conjugations are most of the outer automorphism group, even without the no-sill condition. It means that out is just going to be a finite abelian group.
If it was a graph
So it's
product of finite cyclics.
Right.
If it's a graph product in general, it's going to be abelian.
Right.
But how can you see that from the no-sill? What is the no-sill affecting? Is it affecting these partial conjugations so that they're...
Yeah.
So that they have to be really small and that that's much of the group? Is that the deal?
What we end up doing, what ends up being done is, so we can put some conditions on when these are going to commute with each other, just combinatorially. And that we can use that to build a new graph, which we can call, gamma prime or whatever. And that would give rise to a new graph product. What the paper shows is that graph product is actually all of aught P sigma, that we're not missing any relations. Okay. So this is really cool, and it's a nice way of passing from some basically combinatorial conditions on a graph to very serious algebra about an automorphism group. But the one thing that's, for lack of a better way of putting it, a little unsatisfying is that there's no real geometry that's used here. This is ostensibly a geometric group theory paper where we didn't build a new space, we didn't study a space to get any of this. There's absolutely no geometry going on here. And there's the fact that, as we've already seen from these examples, the no-sill condition is very restrictive. We can't even use it to study a free product. So we have a bit of a problem. So what I wanted to try and do is see if there's some way of attacking this in a more geometric way that hopefully would let us generalize and not have to worry about this no-sill condition so we can study these automorphism groups. So I started looking a bit through the literature to find other places where people are studying an outer automorphism group, because we said that's the only really interesting part of our automorphism group, and where we can, and what kind of spaces they built for them to act on. So we are going to go in order from oldest to newest. How am I doing on time? Okay, I'm going to rush through this a bit. So our first example of this is the mapping class group acting on tight Miller space. So initially from its, I'm not going to get into the definitions of these two objects. I think pretty much everyone in this room knows what those are. If not, talk to me later. or pretty much anyone else in this room. But so initially from these definitions, this doesn't feel like an outer automorphism group acting on anything, just in general. But we have the Dane-Nielsen-Baer theorem that says that the generalized mapping class group is isomorphic to the outer automorphism group of the fundamental group of the surface. So the generalized mapping class group is, instead of just taking the orientation preserving homeomorphisms and modding out by homotopy, we take the full homeomorphism group and up to homotopy or isotopy or whichever definition of the mapping class group you feel like using today. So now we have an outer automorphism group and we have a space that it's acting on. So this is, so far that's really about all I have done in my little bit of surveying the topic here, but this again is pointing me in a nice source of ideas for how to further attack the problem. And that becomes really evident when we go to our next example, a bit less classical. So we have the outer automorphism group of the free group of rank n acting on color-Vogtman outer space. So pretty much everything from here is from a paper by Color and Vogtman from 86. Yes. So what color-Vogtman outer space is, to really simplify it a bit, is just the Teichmüller space of the rows with n petals, or the wedge of n circles, whichever way you feel like defining it this week. So, and again, since we're thinking of it up to homotopy or isotopy or whatever we feel like, however we feel like defining Teichmüller space, the easy way to think of this, because we have a much simpler structure on the object we're looking at the Teichmüller space of, we can really think of it as just normalizing it. So the lengths of all of our edges is always just adds up to 1. It's a much nicer, easier way of thinking of it. So to get a little bit idea of what this is, because we're looking at a much more combinatorial object with the rows of n petals, we can put a very, very natural, easy to see cell structure on outer space. So let's build some of it in rank 2.
And you're allowed to change the topological type, so.
No. Wait, what do you mean? Maybe yes, maybe
not
no.
always a rows with n.
Oh yeah, no, it has to be homotopy equivalent to a rows with n petals.
Yeah, so that's why it's not the same as Teichmüller.
Right. Yeah, this is not the true way it's defined, but it's a really, really good way of thinking of it. Okay, so start with, again, so this is not a rows to begin with, but this is a graph that's homotopy equivalent to rows with 2 petals. And we're going to give this its own 2-cell. So we can think of moving around in this 2-cell as simply changing the lengths of these 3 edges in such a way that we're not actually reducing any of them to 0. Okay? If we were to move completely into an edge, so let's go to this one, that's equivalent to shrinking down one of our other edges.
So that one did go to length 0, but you didn't change the homotopy.
Right, we still haven't changed the homotopy type. We're still homotopy equivalent. But again, we did actually change one of these lengths down to 0. So moving to one of the other edges would be changing a different 1 to 0. This also means that very clearly we can't move to a vertex. If we were to move to a vertex, that would imply we would be changing another edge down to length 0, and now we've changed the homotopy type. So these are open simplices. They have no vertices anywhere. And if we're going to move from, so let's think about this. What we're really doing is trying to build a space for out Fn to act on. So we want to think of this as being sort of, one set of generators, and we can think of an automorphism of the free group as just mapping our set of generators x and y to another set of words in the free group. So when we move from one top-dimensional cell to a different top-dimensional cell, we're really just applying some kind of transvection that's going to be an outer automorphism. So one of those is going to be inverse. Yeah. And again, we can now move around in this cell, and it's going to be changing the length. So moving from one top dimensional cell to another is actually applying one of these outer automorphisms. Moving around in a cell is just, you know, changing the translation length that we're associating to a particular generator and the like. And we can just continue this over and over again. For rank 2, we're really just concerning ourselves with, roughly speaking, 3 different kinds of graphs. An actual rose, which is going to be sitting at an edge. And we have 2 different kinds of valence 3 graphs, which we can think of as sitting in 2 cells. And since we have, you know, clearly 2 different kinds, what you'll find in a lot of pictures, if you look at, you know, it's very easy to find pictures of rank 2 outer space. You'll find that the cells corresponding to the barbells like this tend to be sticking out like this. So it gives us a nicer way of, you know, seeing what's going on and sorting between the different kinds of cells that we've got. Okay, so because of the fact that we can think of this almost like a Teichmuller space, there are a lot of similarities in how the 2 different areas are studied. The best example is the idea of a spine. So at the beginning of the talk, I said that an outer space is a space that the outer automorphism group acts on properly. So as geometric group theorists, we ideally want a geometric action. We want it by isometries, we want it to be proper, and we want it to be co-compact. We don't have co-compact here, and in fact, in the 2 examples that I've given so far, the mapping class group and OutFN, our action isn't co-compact. It's proper, but that's it. Both of these spaces, though, Teichmuller space and outer space, have what we call a spine. It's just a deformation retract such that the action is co-compact. So that is for Teichmuller space, that's due to Thurston in 86. Yeah. I'm still trying to find this exact paper. It is apparently a paper that was written and never published anywhere, except everyone cites it everywhere. I'm still trying to find that. If anyone can help me with that, that would be appreciated. It's apparently never made its way onto the internet.
That in itself.
Right, yeah, that is kind of impressive. And where am I? There we go. And for outer space, that is due to Bryson and Voman in 01. In Bryson and Bowman's paper for constructing a spine for outer space, they actually show something a bit more. They show that the automorphism group of that spine is exactly OutFN. So that deformation retract contains all of the information we care about for OutFN. You know, we don't actually need the full space to study it if all we care about is the group. Another big similarity is that when it comes to studying compactifications of these spaces and their boundaries, we tend to take slightly different definitions of Teichmuller space and outer space than normal. Instead of thinking of it as, for Teichmuller space, the space of hyperbolic structures on a surface homeomorphic to SG, we can think of it as, I'm going to get this messed up, the space of length metrics of group actions of pi1 on its universal cover. And we have a corresponding definition for the free group on the appropriate tree. Both of those, when we're studying their compactifications, we tend to use those definitions instead to look at their compactifications and their boundaries and all of that stuff. So again, a huge amount of similarities between these 2, not incredibly disparate groups. I mean, outer space and Teichmuller space should feel pretty similar. But again, already we have a lot of similarities in how these 2 topics are studied. So we moved from the 30s with Teichmuller space's creation to the 80s for outer space, and now we're going to move to last month. Okay, so we have the outer automorphism group of a right-angled Artin group acting on outer space for a right-angled Artin group. This is from a paper by Ruth Charney, her student Nate Stambaugh, and Karen Feltman, which got in just under the wire of the Mayan apocalypse. on the archive. And they construct an analog of outer space for right-angled Artin groups. Now, this is part 1. There is a part 2 forthcoming. In part 1, they don't quite construct the full outer space. They construct a spine for this subgroup of the full automorphism group to act on. This subgroup, though, is generated by graph symmetries. So, inversions, which, if we're keeping track with what we defined last time, inversions are just our vertex isomorphisms, because all of our vertex groups are going to be Z's in this case. That's the only isomorphism we have. Partial conjugations.
The trivial one.
What? Okay, yes, there's the trivial one. I think we don't care about that, though.
What's a graph symmetry?
A symmetry of the, partial conjugations and non-adjacent transvections. Adjacent. Okay, so the nice thing about this is, for the purpose of studying this to get ideas for studying the case that I'm interested in for right-angled Coxeter groups, this is everything we need already. You know, graph symmetries, great, we're going to have those. Inversions, well, we can just think of that as vertex isomorphisms. Great, we're going to have some of those. Partial conjugations, we said that's the interesting part. And non-adjacent transvections. Well, we don't really care about transvections for the most part. Now, if you remember the definition from earlier, in our case, we can't have non-adjacent transvections because the star of one vertex has to be contained in the star of the other, so we have to have this between adjacent vertices. The conditions for transvections in Artin groups and free groups is very, very different. It involves links and stars instead, so you can have non-adjacent and adjacent transvections. So we don't really care about the rest of the group that they're doing here, at least as far as it goes for what I'm trying to do. And what they do here is they construct a spine directly, keeping in mind that in part 2 of the paper, they'll construct a larger space where we'll see the spine as a deformation retract. The spine that they construct is, at least in my opinion, somewhat reminiscent of McCullough-Miller space for a free product of groups. What they do is they construct blow-ups of the Salvetti complex for their right-angled Artin group. The blow-ups are constructed keeping in mind Whitehead automorphism groups of the free group that pass to actual automorphisms of the Artin group. And they go and put an order on this space of all of these different blow-ups according to the idea of if you can contract a certain kind of hyperplane to get from one blow-up to a different blow-up, then one blow-up of a Salvetti is greater than another. Now that you have a poset, you can take its simplicial realization. Once you have its simplicial realization, they go and show that it's contractible and that the action of out L on it is going to be proper. So all of that is in this paper, which has a nice simple title of Outer Space for Artin groups, so really easy to find. So both this and whenever that second paper comes out, I haven't seen it yet. There isn't like a release date announced or anything like that. So both of them are something I definitely plan on studying quite a bit more. But now on to my idea. So the one big difference between pretty much everything that I've talked about that exists in the literature and studying the equivalent for right-angled Coxeter groups is torsion. None of these have torsion. Or I think, no. I think the mapping class group does have some torsion in it, but like not a lot that we really care about. But in a right-angled Coxeter group, there's torsion all over the place. It's huge. So in all three of these cases, they take a similar approach. We want a place for out W gamma, so out the outer automorphism group of a right-angled Coxeter group. We want a space for it to act on. So the first thing that they do in all of these examples is they find some nice little compact space that has fundamental group, your starting group. Well, this is generated by inversions that commute in a certain way. So there's sort of two places to look. The first one is, okay, well, what's something that has fundamental group Z mod 2Z? RP2, and you'd have to find some way of gluing them together in a weird way, and that's already sounding like a horrible mess to me. The other thing is not to necessarily think about just surfaces or topological, surfaces, but to think about orbifolds. So if we take, so W gamma has P of gamma, totally. So W gamma will act on its appropriate Davis complex on the universal cover of it, and when we mod out by that, we normally would think of just having, some little cell complex, that is some cube complex, that's going to be our strict fundamental domain. Well, instead of thinking of it as that, example, so let's go back to that first graph that I drew, but now let's just think of this as a Coxeter group, so all of these are labeled with 2s. We want to draw this as our strict fundamental domain, but instead of thinking of it quite like that, we want to actually label, here we go. We want to label the places that are fixed by the various generators. And now this is looking almost like an orbifold. There are certain what did we do? We took some simply connected space, we modded out by a group acting geometrically, and we got something else, and we just sort of label where those fixed points are. And those are going to give us little finite isotropy groups. So this is pretty much just a cell complex analog of an orbifold. And now that we have, and by how we define the fundamental group for an orbifold, the fundamental group for this orbicell complex would be our right-angled Coxeter group. So plan A that I have is literally just trying to take the road of Teichmüller space and outer space from here. Try finding different ways I can metrize this, because this has a nice cell structure on it naturally. I'd like to think maybe I can get a nice cell structure on the outer space there in the same way that you do for Kohler-Voigtmann outer space. So that's plan 1. Plan 2 involves this, the overall look of this is very similar to the definition of a complex of groups from Bridson and Heffliger. So again, that's something that got brought to my attention fairly recently, so that's something I plan on studying a bit more to get an idea of how that works, to see how that might influence this. The other idea is to, again, look at the other approach that people take when they're studying Teichmüller space and outer space, of looking at it as the space of length functions of actions of our Coxeter group on the Davis complex, and seeing if by using that definition instead, I might be able to put some natural structure on it and get a nice proper action of the outer automorphism group there. Obviously, as I said before, and I want to reiterate, torsion is sort of the big problem. That's kind of the big unknown here. How is torsion going to affect it? And one other idea that came up recently is we know that if I have some right-angled Artin group, A gamma, that I can construct some W gamma prime such that these are commensurable. The other way is definitely not always true. For example, if I just take some hyperbolic Coxeter group, that's obviously not going to happen. If it's hyperbolic, there can't possibly be a Z plus Z subgroup in it, and this is either going to be free or contain a Z plus Z at the very least. But we might be able to find conditions where the other direction does actually work, and if so, then I can start using what Charney, Stenbaugh, and Voigtmann have already done, and see if there's some way that I can enhance or extend or reflect in some way the outer space they've already created, and see what happens from there. So those so far are the ideas that I have for attacking this problem, and thank you.